Welcome to the second part of the lecture UV-Visible Spectroscopy, Law of Photometry. The learning outcome: the learner will be able to understand Lamberts Law, relate Lamberts Law to quantitative determinations, explain derivations and deviations of Beer's and Lamberts Law, perform the determination of concentration of unknown using this law, and list the applications of UV visible spectroscopy. Previous review of the lecture. We have studied the UV visible region in previous lecture. It is divided in three parts: near vacuum UV, that is 10 to 200 nanometer, near UV 200 to 400 nanometer, and visible region, that is 400 to 750 nanometer. We also studied the principle of spectroscopy and UV visible spectrum. In case of UV visible spectrum, it is a plot of absorbance on y-axis and wavelength on x-axis, where we are determining the lambda max, that is the wavelength at which maximum absorption is observed. So we have studied the different types of electronic transactions involved in UV visible spectroscopy. Basically, four transactions we have studied according to the need of energy. That is, first one was sigma to sigma strike transaction. Second was N to sigma strike transaction. Third one was pi to pi strike transaction. And fourth one was N to pi strike transactions. So these transactions are electronic transaction. Therefore, the spectroscopy was also known as electronic spectroscopy. Then we have studied the definitions of chromophore, then oxochrome. We have studied the bathochromic shift and hypsochromic shift. Chromophore, these are the unsaturated group responsible for absorption of the radiations. Two types: dependent chromophore, independent chromophore. Oxochrome, these are the saturated group with lone pair of electron when attached to the chromophore alter the intensity of absorption. Then we have studied the bathochromic and hypsochromic shift. Bathochromic shift, also known as the red shift, shift of the lambda max toward the higher side. Hypsochromic shift, shift of the lambda max towards the lower side, that is blue side, therefore also known as the blue shift. Then we have studied the effect of solvent, what sort of solvents we should use, that is choice of solvent, that depends upon the absorption of solvent in the range. So we have studied the cutoff wavelengths of various solvent which is to be selected for ultraviolet visible spectroscopy. Today we'll start with the law of light absorption. So Beer's law was independently discovered in various forms by Pierre Bauger in 1729, John Heinrich Lambert in 1760, and August Beer in 1852. This is in optics the Beer-Lamberts law, also known as Beer's law or Beer-Lamberts-Bauger's law, is an empirical relationship relating the absorption of light to the properties of material when the light is traveling through it. So fundamental law of the photometry when we are studying, so we have to see the absorption spectroscopy, which is the measurement of absorption of electromagnetic radiation of definite and narrow wavelength. Generally, for this purpose, we are using the monochromatic light. Monochromatic means single, chrome means color, and if it is not single color, we are using the band of light that is known as a narrow bandwidth by a molecules or atoms or ions or particular substances. When a beam of light incidents on a homogeneous medium, a part of incident light is reflected, denoted as IR. A part of incident light is absorbed, denoted as IA, and a part is transmitted, denoted as IT. So we can write the equation that I, that is intensity of the transmitted beam, intensity of the bombarded beam, will be equals to the intensity of the reflected beam plus intensity of the absorbed beam and intensity of transmitted beam. Actually, in determination, we are keeping this reflection minimum by designing the instrument such that there will be no effect of reflection of the light. So only two phenomena will occur, that is, either there will be the absorption or there will be the transmission. Actually, we are not able to measure the absorbance by using any instrument. What we can measure, the intensity of the transmitted beam and the intensity of the bombarded beam. The difference of these two intensities will give you the information regarding the intensity of the absorbed radiation. So we are interested in intensity of the absorbed radiation. So initially the Baugers and the Lamberts law was developed. So when a monochromatic light passes through an absorbing medium at a right angle to a plane of the surface of the medium, the rate of decrease in intensity, what I am saying, the rate of decrease in intensity of radiation is proportional to the thickness of medium. So if you see this thickness of the medium, as we are increasing this thickness, the intensity of the transmitted beam decreases. So I0 is the intensity of the incident beam. So as it passes through the medium, that is decreasing. So I is the IT, we can call it as a intensity of the transmitted beam. So B, we will term it as a thickness of the medium. Even if you are observing P0, I will consider it as a I0. So this is the Lambert's law, which is related to the solid medium, where the thickness of medium will decrease the intensity of the transmitted beam. So mathematically, we can prove or represent the Lambert's law in this way. Minus di upon dB is directly proportional to the intensity. This minus indicates the decrease in intensity. As we are there, you are studying the decrease in intensity, we have to use this minus sign. Di upon dB, B is a path length, is directly proportional to the intensity of the incident light. To take out this proportionality sign, we have to include a constant called as a K. So now we can write di upon dB is equals to the Ki, where B is the thickness of the medium and K is a proportionality constant. By processing mathematically, that is by integrating above equation, a limit of 0 to B. 0 to B is a path length which is starting from 0 and ending with a particular thickness B. We get the equation like this. Then when we are solving this integration, we'll get one natural logarithm equation, ln I0 upon IT equals to KB. So now, where I0 is the intensity of incident light, IT is the intensity of transmitted light, and K is a constant which depends upon the wavelength. By changing to the common logarithm, this is ln, that is a log e to the base log e. Now we'll consider this to the log 10. So IT equals to I0 minus to the rest minus 0.4343 kb. So this minus 0.4343 can also be included in this K value, that is constant value. So we will get a modified equation IT equals to I0 minus KB. So this is we will consider as a Lambert's law equation 1. So we have to combine these two equations together, Lambert's law equations and Beer's law equation, in next slide. So now we'll go towards the Beer's law. We have seen that the Lambert's law is for the solid substances, solid when the light is passing through the solid. Beer's law is for the solutions. The intensity of transmitted beam of a monochromatic light decreases exponentially with increase in concentration of absorbing substances arithmetically. Here also, so the path length is the by holding the liquid in the cuvette, and the concentration of that liquid will result into the change in intensity of the transmitted beam, and that we are measuring in the Beer's law. So as we are increasing the concentration, the intensity of transmitted beam will decrease. So here also we have to mathematically derive this equation. So mathematical representations of Beer's law we can write in the same way. There we are using the B as a path length. Here we will use C as a concentration. The rest of the things will be same. Minus di upon dc is directly proportional to the I, that is intensity. So to take out this proportionality sign, we can include a proportionality constant, that is k dash, that is called as the proportionality constant. So minus di upon dc equals to k dash I. Now we will integrate this in the limits of 0 to c, because we are changing the concentration from 0 to c. So we will integrate this equation. So mathematically, if you integrate the equation, we'll get to a natural logarithm equation, that is ln I0 upon IT equals to k dash c, where I0 is the intensity of incident light, IT is the thickness of medium, and k dash is a constant which depends upon the wavelength. By changing to the common logarithm, that is to the base 10, we will get the value again. It equals to I0 to the base 10 minus 0.4343 k dash c. So this minus 4343 can be included in k dash, and we'll get the modified equation that it equals to I0 minus k dash c. So this is the second equation that is generally called as a Beer's law equation. So we have to combine this equation 1 of the Lamberts law and equation 2 of the Beer's law, because we are using a solution which is to be kept into the solid cuvettes. So effect of both is to be considered. So it is a combined equation that is called as a Beer's Lamberts law equation. So by combining equation 1 and 2, we get a final equation it equals to I0 to the base 10 epsilon Cb, where this epsilon is called as a molar absorptivity, and this constant, it is a combined constant of k and k dash. If we combine this k and k dash, it gives you the value of epsilon, and that is called as a molar absorptivity. C is the concentration and B is the thickness of the medium, that is the path length. So we get this equation it equals to I0 to the base 10 epsilon Cb. The above equation can be written as log of, if we multiply by the log of I0 upon IT equals to epsilon BC. Okay, so just we take out this sign, we take this sign to the other side, and if it is a I0 upon IT, we can convert it is a IT upon I0, it can be converted to the I0 upon IT. So this is mathematical simplification. You just go through the mathematical simplification, you will get this equation. Log of I0 upon IT equals to epsilon BC. So log of I0 upon IT is generally called as absorbance, that is denoted by capital A. Therefore, we can also write A equals to epsilon BC. Epsilon is a molar absorptivity, B is a path length, and C is a concentration. One more equation we are taking, that A equals to ABC. What is the difference between these two values? These are two, all are constant. Epsilon is also constant, and this small a called as absorptivity, this is also constant. So this constant depends upon what type of the concentration unit you are using. If the concentration unit is gram moles per liter, it is called as a molar absorptivity. Okay, so the concentration unit in this case will be gram moles per liter. If the concentration unit is grams per liter, it is called as a absorptivity. So this unit of this constant depends upon what type of the concentration unit you are using. The amount of radiation absorbed may be measured in number of ways. So this will required for quantitative estimation using the Lamberts law. So all these equations you have to by heart, that you will require. So generally, either we are measuring the absorbance or we are measuring the transmittance, T. So we can write T equals to I upon I0, intensity of the incident beam and intensity of the transmitted beam. So this transmittance is generally taken in the form of the percent transmission. So we'll write percent transmission equals to 100 into the T. Now we can calculate this absorbance. As we know, absorbance equals to log of I0 upon IT, and by how we can convert it into the transmittance unit. So A equals to log of 1 by T. Okay, so it will be log of 1 by T, as we are using the percentage value of the transmittance. So it will be A equals to log of 100 by percent T. Log of 100 is known as a 2. Okay, so if we simplify this equation, we'll get a major equation A equals to 2 minus log percent T. So these are all equations you required in the quantitative estimations. So we are going to have some examples on Lamberts law calculations, and that you will use practically in your laboratory also to calculate the various concentration. One more thing or unit we are using in UV visible spectroscopy, that is A11. A11 is the absorbance. Okay, so it is the absorbance of 1% solution in 1 centimeter path length. That is called as a A11 value. Okay, it is not the molar absorbance. It is a A11 absorbance. It is a absorbance of 1% solution in 1 centimeter path length. So that can be calculated by dividing the observed absorbance by the path length and concentration. See the unit of concentration. It is a 1% solution. Percent means grams per 100 ml. So the concentration unit will be grams per 100 ml. So why I am insisting on the unit of concentration? Because this unit you will use in various calculations. So here the unit is gram moles per liter in case of molar absorptivity. In absorptivity it is grams per liter, and in case of the A11 it is grams per 100 ml. You have to remember these concentration units. Now, what is the significance of Beer's law? So we have this equation A equals to epsilon BC. So as we are discussing, we can calculate this concentration. So just A equals to epsilon A upon epsilon B will be equals to the concentration. So to know the concentration of unknown species, we can use this equation where A is absorbance. So A absorbance, it is a ratio of intensities of light log of I0 upon I. So it will not having any unit. Epsilon is a molar absorptivity with units of moles inverse, moles liter inverse, centimeter inverse, because it is a gram moles per liter. So therefore it is known as a gram moles per liter per centimeter. B is a path length of the sample, that is a path length of the cuvette in which the sample is contained. So we will express this measurement in centimeters. All the path length is in the centimeter. C is the concentration of compound in solution expressed in moles per liter, because we are using epsilon as a value. If you are taking small a absorptivity of value, the concentration will be grams per liter. The reason why we prefer to express the law with this equation, because the absorbance is directly proportional to the other parameter. So as the absorbance increases, your concentration increases, path length increases, molar absorptivity increases till it obeys the Beer's law. So Beer's law also has certain limitations that we have to study. So what are the limitations to Beer's law? So the law tends to break down at a very high concentration. Beer's law is only followed by very dilute solutions. At high concentration, it does not follow, especially if material is highly scattering. If it is a colored and highly scattering, it will not obey the law of Beer's law, that is, intensity of transmitted beam decreases exponentially with increase in concentration of absorbing solution arithmetically. Means as the concentration of the absorbing solution increases, the intensity of the transmitted beam should decrease or absorbance should increase. If the light is especially intense, nonlinear optical process can also causes the variations. So we have to use a specific bandwidth of the radiations and a monochromatic light for the determination. So if you plot the concentration versus absorbance, you will get the graph like this. Up to a certain concentration, it obeys the Beer's law, means the values remain in linearity. After this concentration, after a particular concentration, the values will not come onto the straight line, indicating that Beer's law is followed up to this concentration only. After this, the Beer's law is not followed. That is the limitations to Beer's law. So when we are thinking of the limitations, we have to first think that Lambert's law. So there are no exceptions or limitations to Lambert's law. Why? Because we are using the match pair of the cells or cuvettes. Match pair means there is no change into the path length of light. Path length of light remain same for sample as well as for the standard. It is not varying. So there will be no limitations to Lambert's law. Only limitations will be observed to the Beer's law. So there are three types of the limitations which were observed to the Beer's law. First one is known as a true deviation, that is known as a concentration deviation. Second one is your instrumental deviation, and third one is your chemical deviation. So now we'll see one by one. First is called as a true deviation or concentration deviation. Dilute solutions only follows this law. When concentration is high, the molecule will react or interact with each other by collision, and each molecule will not absorb radiation energy in same manner as it does in the dilute solution. So when the concentration increases, it will not absorb the radiations in same quantities, and there may be the collision at the higher concentration, resulting in unequal distribution of radiation throughout the solution. So therefore, it will not maintain the linearity at the higher concentration. We have to go for the dilute solutions only. Second one, that as the concentration increases, index of refraction also changes. So absorbing species changes at the higher concentration, the refractive index changes, and that result into the deviations in the Lamberts law. So this is the first deviation. Second one is your instrumental deviation, which is dealing with the ability of your instrument. First is due to the stray radiation reaching the detector. So what do you mean by stray radiation? Stray radiation means the radiations, unwanted radiation which are reaching to the detector. Your detector compartment is designed in such a way that no external light should reach to the detector. If you are keeping your compartment open without closing it with the lid, it may result into the entry of the external light, and that may causes the deviation. Means once you are adjusted 0 and 100 of your instrument, and if you are getting more than 100 reading, that may be due to this. More than 100 reading means if you are taking solvent and you are adjusting your instrument to read 100 with the solvent, 100% transmission. Okay, so and if the reading is more than 100, it indicates that some stray lights are there or some faults are there with the instrument. So the fault may be due to the sensitivity changes of the detector employed. Many times due to the long uses, the sensitivity of the detector changes, and it will not maintain the 100 value. Even if you are not doing anything, the detector will respond differently and will produce the deviation. Then fluctuation of the radiation source. Whatever source we are using, if the intensity of the sources changes, it gives you the different intensities of the light after the different time period. Okay, due to the heating, some resistance will decrease, and that causes the fluctuation in the intensities. That will also leads to the deviation. So these are the instrumental deviation. Second is defect in the radiation amplification system, that is to the hardware part of the instrument. Then working in a broad band of the wavelength rather than the monochromatic radiation. So all law which we are studying, we are considering it as a monochromatic radiation, radiations of the single wavelength or single band we are using for the purpose. Third one is your chemical deviation, that is reaction that causes the change in the absorbance of the solution. Absorbing species may undergo ionization, dissociation, or even may react with the solvent or each other. So hydrolysis may be taking place with the solvent like water, and that may changes the intensity of the transmitted beam. Reaction may produce two or more species in the solution with varying absorptivity values, and that result into the deviation. So how we can rectify or overcome this deviation? This can be corrected using buffers. Okay, so if the pH changes is there, you can have the buffer in your solution. Selecting suitable solvent. If we are not able to use water as a solvent, we can go for methanol or some other solvents can be used. An appropriate band of the wavelength. Okay, we have to work with the narrow band width or narrow band of the radiation. Then this problem can be overcome. So this is the chemical deviation. So up till now we have studied the Lamberts law, how it is to be stated. Then what are the deviations of Lamberts law? We will have some examples of the problems Okay, so some numericals I will show you here. So by observing these numericals, you can actually perform this calculations in your laboratory. So first numerical, calculate the concentration of methyl testosterone in ethanol solution giving absorbance of 0.890 in 1 centimeter cell at lambda max value of 241 nanometer. The additional things which are given with the problem, that A11 value in BP monograph of methyl testosterone is 540 at 241 nanometer. So these things is asked, and you have asked to calculate the concentration of methyl testosterone in ethanol solution. Okay, so you have to be very careful. You just read the problem carefully and observe what quantities has been given. Many students start the calculations with lambda max. So lambda max values, that is not to be used in any calculation step. Okay, so you just observe or read the problem carefully and you note down what is given. In above problem, we can see that A is given, capital A, that is absorbance 0.890. B is given, that is your path length, that is 1 centimeter. And one more value is given, that is 540, that is called as A11. Okay, you see that slide which we have done in the previous. So various equations are given on the slide. Okay, so we have one equation, that is A11 equals to A upon BC. So that equation we can use to calculate the concentration here. We can modify this equation. So this is for the uh, absorbance of 1% solution in 1 centimeter path length. We can convert this equation to calculate the concentration. So C equals to A upon B into A11. So we can just modify this equation to get this new modified equation. Now you have the value of absorbance, you have the value of the path length, and you have the value of A11. Just put the values in the equation and you will get the answer. Okay, so if you put the values, you will get 0.165. Now the important thing is the unit of your answer. Okay, so here calculations, just they are ask you the concentration, they are not asked in the any particular unit. So when you are calculating the concentration, we are using this A11 value. So A11 value, when the concentration is in the percent, that is grams per 100 ml. So your answer should also have the same unit, that is grams per 100 ml. So your answer is 0.165%, that is grams per 100 ml. So this is one illustration. I have the four different types of problems for you. The second illustration we'll just see Beer Lamberts Law problem 2. Calculate the concentration in microgram per ml of the drug, okay, whose molecular weight is 204.2 in 1 molar hydrochloric acid, giving absorbance of 0.613 in 4 centimeter cell at lambda max value of 277 nanometer. The molar absorptivity value, see here, they are given the molar absorptivity value is 5432 at 277 nanometer. Okay, we don't have to do anything with the lambda max value, that is 277 nanometer. Rest of the things you just read the problems once again to see what exact quantities are given in the problem. So what is the given? Given is first your, see, this molecular weight is given. We'll take it later on. 1 molar HCl. Solvent molarity is not important for us. The next important quantity is given. That is 0.613. That is the absorbance. B is given as a path length. That is 4 centimeter. Okay. And the epsilon is given directly. Epsilon equals to 5432. Now again recall the equations which is there on that slide. So which equations we can use? A equals to epsilon BC, correct? We can use this equation, A equals to epsilon BC. Now we can convert this equation to calculate the concentration. Okay, so if you take this epsilon B in the denominator, okay, if you divide this absorbance with the path length and molar absorptivity, you will get the concentration. Now you recall the unit of concentration. What will be the unit of concentration here? As we are using the molar absorptivity value, the unit of concentration will be, yes, gram moles per liter. Now see here, put the values in the equation. C equals to 0.613 divided by 4 into 5432. So we'll get some values like this: 2.82 into 10 raised to minus 5 moles per liter, because we are using the epsilon molar absorptivity value. Your result should be moles per liter. Now see, in our problem they ask us to find out the concentration in microgram per liter, microgram per ml of the drug. Okay, so we have to convert this moles per liter to microgram per ml. Okay, do you know how to convert? The moles per liter can be converted into the grams per liter by multiplying with the molecular weight. See the importance of molecular weight, which is given in problem. So why it is given? To multiply with the moles per liter. Okay, so we will take 2.82 into 10 raised to minus 5 and we will multiply with 204.2. So here we'll get the concentration in grams per liter as 5.76 into 10 raised to minus 3. Okay, so 10 raised to minus 3 means it is 0.00576 grams per liter. So we had to convert this grams per liter into the micrograms per ml, that is multiplying by 10 raised to 6. Okay, so if you multiply it by 10 raised to 6, it will be 5.76 microgram per ml. So your answer is 5.76 microgram per ml. So in this way, what quantities are given and which equation to be used, that can be used to calculate the answer of this problem. So this is illustration 2. Now we'll go for the illustration 3. So see the problems one again. An absorbing spectrum of titanium dioxide complex at 400 nanometer gives absorbance of 0.456 when concentration is given 32 microgram per ml solution is taken. Okay. Now unknown solution treated in identical fashion, means we are having the same path length, same absorptivity values or molar absorptivity values. So unknown solution treated in identical fashion gives an absorbance of 0.501. Assuming identical cell, find out unknown concentration. Okay, so see, read the problem once again and find out what is given in the problem. So the given things we can find out. We have 1A1, okay, absorbance of the one substance, that is 0.456. Then we have the concentration, that is 32. Okay, then we have the absorbance of the second substance, that is 0.501, that is called as the unknown. Okay, so which formula we can use? A equals to ABC. Okay, we know, all of you know that we have one formula, A equals to ABC. So if we want to compare the two substances, we can use the same formula to show the absorbance of two substances. So we can convert this formula. A1 equals to capital A1 equals to small a1 B1 C1. Okay, so absorbance equals to absorptivity into path length into the concentration. In same fashion, A2 equals to A2, B2 and C2. Now we are using the same conditions, that is the same path length and same absorptivity value. So these two will be vanishing. So we can divide A1 upon A2 equals to A1 upon B, A1 into B1 upon into C1 divided by A2 into B2 into C2. As these two A1 and A1 B1 and A2 B2 are same, the modified equation will be A1 upon A2 equals to C1 upon C2. Now you cross multiply this equation. Okay, so what you will get? If you cross multiply the equation, you will get A1 into C2. See this, A1 is multiplied by C2 equals to A2 multiplied by C1. Okay, if you want to calculate the concentration of unknown C2, so we can modify these equations again. C2 equals to A2 into C1 divided by A1. This A1 will be in this part, it will be getting divided. Okay, so you will have this new equation C2 equals to A2 into C1 upon A1. Now see our given things. What we have? We have the A1 values, we have the A2 values, and we have the concentration values. Just put the values in the equation. So C2 equals to 32, that is concentration, into absorbance of your sample, that is 501, divided by absorbance of your standard, that is 0.456. So you will get a concentration. So again think what will be the unit of concentration. Here we are comparing the standard and sample together. Definitely the unit will be the unit of your standard. So unit of standard was microgram per ml. So your sample will also be in the microgram per ml. So you will get the result of concentration, that is 35.157 microgram per ml. In this way, the third type of the problems we can solve by using the Lamberts law. The fourth illustration with the different quantities we will see now. A sample in 1 centimeter cell is determined by a spectrophotometer to transmit 80% of light at certain wavelength. If absorptivity of substance at this wavelength is 2, then what is the concentration? Okay, read the problem once again very carefully and find out what is given. So given A, that is your absorptivity. Okay, so see here, the absorptivity, this is small a, the absorptivity of substance at this wavelength is 2. So we have the absorptivity value. Then B, path length, that is 1 centimeter. And we have the percent T values, that is 80. Now you again go to that slide and see what equations we can use. We have one equation, A equals to 2 minus log percent T. So first of all, we have to find out the absorbance. To find out the absorbance, we have one equation, 2 minus log percent T. So because we are having the percentage T values, that is 80. So 2 minus log of 80. If you solve this, you will get the unit, and you will get the value 0.097. Now what you have to do? You have to use the equation A equals to ABC, because we have absorptivity value, we have path length, and now we have calculated the absorbance. So this is the equation which we can use. Now they are asked us to find out the concentration. So we will modify this equation to measure the concentration. So concentration equals to A upon BC. Okay, now put the values of absorbance, that is 0.097 divided by path length into the absorptivity value. So this is the absorptivity value and this is the path length. In this way, we can calculate the concentration of anything. So the concentration is 0.0465. Now we are using the absorptivity values here. Okay, small a. The small a is given absorptivity. Now you recall that what I am saying, the concentration of absorptivity, the concentration unit in case of absorptivity will be grams per liter. So your answer should be in the grams per liter. Understood? So these are the four problems what we are studying. Now we have observed many applications of UV visible spectroscopy up till now. Can you list those applications in the notebook before you proceed to the next part? So just pause this video and write down your observations in the notebook. I think all of you have written the observations. Now play the video and check your answers with what is listed here. So applications of UV visible spectroscopy, we can write the various applications in this way. The first is your quantitative analysis. UV absorption spectroscopy can be used for quantitative determination of compound that absorb the ultraviolet radiation. What is the requirement? That it should use to absorb the ultraviolet radiation. The determination is based on Beer Lamberts law. So we have done some examples by using Beer Lamberts law, and we are determining the concentration in either grams per liter, moles per liter, or in percentage, or in microgram per ml. So certain unit we will use, and that is quantitative units. So it is useful for the quantitative analysis. The second example is your qualitative analysis. Ultraviolet absorption spectroscopy can be used for characterize those type of the compound which absorb UV radiations. So this is the use for the identification. So identification is done by comparing the absorption spectrum with the spectra of known compounds. Just we'll have one known compound spectra and unknown compound spectra. We can compare those spectra and we can do the identification. UV absorption spectroscopy is generally used for characterizing aromatic compounds and aromatic olefins. One more example of qualitative estimation is a detection of the impurities. Okay, so we can use this for the detection of the impurities. UV absorption spectroscopy is one of the best method for determination of the impurities in organic molecule. Additional peak can be observed due to the impurities in the sample, and it can be compared with that of the standard raw material. Okay, so we will have one examples that benzene appears as a common impurity in cyclohexane. Its presence can be easily detected by its absorbance at 255 nanometer as impurity. Okay, so this is the qualitative estimations for detection of the impurities. In the structural elucidation of organic compound, the next application is in the structural elucidation. So UV spectroscopy is useful in structural elucidation of organic molecule. The presence or absence of unsaturation, okay, unsaturation, that is double bond. The presence of heteroatoms, that is oxygen, nitrogen, sulfur with a lone pair of electron, can be detected by using the UV visible spectroscopy in the structural elucidation, that is determination of the structure of molecule. From the location of peak and combination of peak, it can be concluded that whether the compound is saturated or unsaturated. That also can be detected by using the position. So heteroatoms are present or not present, that can also be detected in the structural isolation process using the UV visible spectroscopy. The next one is the dissociation constant of acids and bases. So we can use the pH values to detect the dissociation constant of acids and bases. That one is more one example. In the practical also we are doing this determination of dissociation constant by using this UV visible spectrophotometer. The next biochemical application, that is chemical kinetics. In many chemical reaction, the kinetics of the reactions can be studied by using this UV visible spectroscope. The next one is your quantitative analysis of the pharmaceutical substances, impurities, or the concentration of active substances in the final formulations can be detected by using this UV visible spectroscopy. Uh, the sample is to be analyzed for its content, percentage purity. Then one more example, that is determination of molecular weight. Molecular weight can be determined by using your UV visible spectroscopy. The next application is it can be used as a detector in HPLC, that is high performance liquid chromatography. The sample which is coming out from the column as a separated species can be detected using UV visible spectrophotometer. So it is used as a detector. And the last one is the multi-component spectrophotometric analysis, where in the combination we can determine the substance using the ultraviolet visible spectroscopic method. So there are various multi-component methods that are used, such as using absorption correction method, then either we can go for the solvent extraction of the sample, then of the multi-component solution, and then we can determine, or we can go for the simultaneous equation method, where we can keep the samples together to determine the concentration. One more method is the absorption ratio method to determine the concentration. Another one is the geometric correction method and orthogonal polynomial methods. So these are the various multi-component spectrophotometric methods which are used for detection of the concentration of multi-component species. One application is the spectrophotometric titrations, which can be used to determine the concentration of reacting species. Either this concentration of reacting species increases or decreases, that result into the change in concentration or change in absorbance values, and that can be quantitatively detected by using this UV visible spectroscopy. So these are all applications of UV visible spectroscopy. Now in the next lecture, we'll start with the instrumentation or general instrumentation of UV visible spectroscopy. So thank you and see you in the next lecture. Happy learning. Thank you to all.